Greetings, I'm Salvador Cordova. Welcome to this first lecture, Lecture 1.1 in the college level General Chemistry lecture series presented by the Evidence Reasons Academy. The material covered in this video is almost verbatim from the OpenStax General Chemistry book 2E and is reproduced here in this video under a Creative Commons License 4.0 as detailed in the video description. Thank you for joining me today. One way to learn or relearn something is to teach it, and learning by teaching is one of the reasons that motivated me to make this series of chemistry videos. But the other reason I'm creating this video series is to serve our channel's viewers with high quality, free of charge science education. In my opinion, what is offered in these free videos is worth far more than an entire bachelor's degree in certain disciplines at certain universities, like Duke University, which charges over $250,000 to get a bachelor's degree in certain so-called social science disciplines of deeply questionable scholarly value. With that, let's dive right into Lecture 1.1 from OpenStax. 1.1, Chemistry in Context. Learning objectives. By the end of this section, you will be able to outline the historical development of chemistry, provide examples of the importance of chemistry in everyday life, describe the scientific method, differentiate among hypotheses, theories, and laws, provide examples illustrating macroscopic, microscopic, and symbolic domains. Throughout human history, people have tried to convert matter into more useful forms. Our Stone Age ancestors chipped pieces of flint into useful tools and carved wood into statues and toys. These endeavors involved changing the shape of a substance without changing the substance itself. But as our knowledge increased, humans began to change the composition of the substances as well. Clay was converted into pottery. Hides were cured to make garments. Copper ores were transformed into copper tools and weapons, and grain was made into bread. Humans began to practice chemistry when they learned to control fire and use it to cook, make pottery, and smelt metals. Subsequently, they began to separate and use specific components of matter. A variety of drugs such as aloe, myrrh, and opium were isolated from plants. Dyes such as indigo and Tyrian purple were extracted from plant and animal matter. Metals were combined to form alloys. For example, copper and tin were mixed together to make bronze, and more elaborate smelting techniques produced iron. Alkalis were extracted from ashes, and soaps were prepared by combining these alkalis with fats. Alcohol was produced by fermentation and purified by distillation. Attempts to understand the behavior of matter extended back for more than 2,500 years. As early as the 6th century BC, Greek philosophers discussed the system in which water was the basis of all things. You may have heard of the Greek postulate that matter consists of 4 elements: earth, air, fire, and water. Subsequently, an amalgamation of chemical technologies and philosophical speculations was spread from Egypt, China, and the Eastern Mediterranean by alchemists who endeavored to transform quote-unquote base metals such as lead into quote-unquote noble metals like gold, and to create elixirs to cure disease and extend life. And it references figure 1.2. Figure 1.2, this portrayal shows an alchemist's workshop circa 1580. Although alchemy made some useful contributions to how to manipulate matter, it was not scientific by modern standards. Credit the Chemical Heritage Foundation. From alchemy came the historical progressions that led to modern chemistry, the isolation of drugs from natural sources, metallurgy, and the dye industry. Today, chemistry continues to deepen our understanding and improve our ability to harness and control the behavior of matter. Chemistry, the central science. Chemistry is sometimes referred to as the central science due to its interconnectedness with a vast array of other STEM disciplines. STEM stands for areas of study in the science, technology, engineering, and math fields. Chemistry and the language of chemists play vital roles in biology, medicine, materials science, forensics, environmental science, and many other fields. Figure 1.3. Let's take a look at figure 1.3. Figure 1.3. Knowledge of chemistry is central to understanding a wide range of scientific disciplines. This diagram shows just some of the interrelationships between chemistry and other fields. The basic principles of physics are essential for understanding many aspects of chemistry, and there is extensive overlap between many subdisciplines within the two fields, such as chemical physics and nuclear chemistry. Mathematics, computer science, and information theory provide important tools that help us calculate, interpret, describe, and generally make sense of the chemical world. Biology and chemistry converge in biochemistry, which is crucial to understanding many complex factors and processes that keep living organisms, such as us, alive. Chemical engineering, material science, and nanotechnology combine chemical principles and empirical findings to produce useful substances, ranging from gasoline to fabrics to electronics. Agriculture, food science, veterinary science, and brewing and winemaking help provide sustenance in the form of food and drink to the world's population. Medicine, pharmacology, biotechnology, and botany identify and produce substances that help keep us healthy. Environmental science, geology, oceanography, and atmospheric science incorporate many chemical ideas to help us better understand and protect our physical world. Chemical ideas are used to help understand the universe in astronomy and cosmology. That's a beautiful diagram right there. Chemistry is the central science. What are some changes in matter that are essential to daily life? Digesting and assimilating food, synthesizing polymers that are used to make clothing, containers, cookware, and credit cards, and refining crude oil into gasoline and other products are just a few examples. As you proceed through this course, you will discover many different examples of changes in the composition and structure of matter, how to classify these changes and how they occurred, their causes, the changes in energy that accompany them, and the principles and laws involved. As you learn about these things, you will be learning chemistry, the study of the composition, properties, and interactions of matter. The practice of chemistry is not limited to chemistry books or laboratories. It happens whenever someone is involved in changes of matter or in conditions that may lead to such changes. Let me take a brief pause here. That seems to be the definition of what chemistry is, this sentence here. As you learn about these things, you will be learning chemistry, the study of the composition, properties, and interactions of matter. Chemistry, the study of the composition, properties, and interactions of matter. The scientific method. Chemistry is a science based on observation and experimentation. Chemistry is a science based on observation and experimentation. Doing chemistry involves attempting to answer questions and explain observations in terms of the laws and theories of chemistry, using procedures that are accepted by the scientific community. There is no single route to answering a question or explaining an observation, but there is an aspect common to every approach. Each uses knowledge based on experiments, that can be reproduced to verify results. Some routes involve a hypothesis, a tentative explanation of observations that acts as a guide for gathering and checking information. A hypothesis is tested by experimentation, calculation, and/or comparison with the experiments of others, and then refined as needed. Some hypotheses are attempts to explain the behavior that is summarized in laws. The laws of science summarize a vast number of experimental observations and describe or predict some facet of the natural world. If such a hypothesis turns out to be capable of explaining a large body of experimental data, it can reach the status of a theory. Scientific theories are well substantiated, comprehensive, testable explanations of particular aspects of nature. Theories are accepted because they provide satisfactory explanations, but they can be modified if new data become available. The path of discovery that leads from question and observation to law or hypothesis to theory, combined with experimental verification of the hypothesis and any necessary modification of the theory, is called the scientific method. Figure 1.4. The scientific method follows, the scientific method follows a process similar to the one shown in this diagram. All the key components are shown in roughly the right order. Scientific progress is seldom neat and clean. It requires open inquiry and the reworking of questions and ideas in response to findings. So let me just walk through this diagram. We have observations and curiosity. And then we form hypothesis, make predictions, then we perform experiments, make more observations, and then we see if the results are consistent with prediction, and we just keep reiterating. If the results are consistent with prediction, it contributes to body of knowledge. And further testing does not support hypothesis, we go back if it doesn't contribute. So much additional testing yields constant observations. Observations become law. Much additional testing supports hypothesis. Hypothesis becomes theory. Let me just pause a little bit. The distinction between law and theory might need to be a little bit more developed. That's certainly not something that that distinction wasn't anything that was made in my undergraduate or graduate studies, but let's just move forward. This is an interesting, that's an interesting distinction between a law and a theory. In physics, a lot of what we study are laws. I mean, so much of learning in physics is actually studying of laws. Anyway, the domains of chemistry. Chemists study and describe the behavior of matter and energy in three different domains: macroscopic, microscopic, and symbolic. These domains, let me increase the size here. These domains provide different ways of considering and describing chemical behavior. Macro is a Greek word that means large. The macroscopic domain is familiar to us. It is the realm of everyday things that are large enough to be sensed directly by human sight or touch. In daily life, this includes the food you eat and the breeze you feel on your face. The macroscopic domain includes everyday and laboratory chemistry, where we observe and measure physical and chemical properties such as density, solubility, and flammability. Micro comes from the Greek and means small. The microscopic domain of chemistry is often visited in the imagination. Some aspects of the microscopic domain are visible through standard optical microscopes. For example, many biological cells. More sophisticated instruments are capable of imaging even smaller entities such as molecules and atoms. See figure 1.5b. Let's take a look at figure 1.5b. Okay, 1.5b. There it is. These, you can see my cursor here. These are molecules. That's H2O gas, H2O solid, and H2O liquid. And let's see the caption B. At the molecular level, the microscopic domain, gas molecules are far apart and disorganized. Solid water molecules are close together and organized, and liquid molecules are close together and disorganized. However, most of the subjects in the microscopic domain of chemistry are too small to be seen even with the most advanced microscopes and may only be pictured in the mind. Other components of the microscopic domain include ions and electrons, protons and neutrons, and chemical bonds, each of which is far too small to see. The symbolic domain contains the specialized language used to represent components of the macroscopic and microscopic domains. Chemical symbols, such as those used in the periodic table, chemical formulas, and chemical equations, are part of the symbolic domain, as are graphs, drawings, and calculations. These symbols play an important role in chemistry because they help interpret the behavior of the macroscopic domain in terms of the components of the microscopic domain. One of the challenges for students learning chemistry is recognizing that the same symbols can represent different things in the macroscopic and microscopic domains. And one of the features that makes chemistry fascinating is the use of a domain that must be imagined to explain behavior in a domain that can be observed. Let me repeat that. This is interesting. One of the features that makes chemistry fascinating is the use of a domain that must be imagined to explain behavior in a domain that can be observed. A helpful way to understand the three domains is via the essential and ubiquitous substance of water. That water is a liquid at moderate temperatures, will freeze to form a solid at lower temperatures, and boil to form a gas at higher temperatures. Figure 1.5. So let's look at figure 1.5. Oh, that's a beautiful picture right there. We have a picture here where we have liquid water, and then we have solid water, ice, and then we have gaseous water. Well, maybe you can't see it. We have water droplets up here. Let's see what the caption says. Moisture in the air, icebergs, and ocean represent water in the macroscopic domain. Now they have H2O gas. Technically, I don't think, someone correct me on this, I don't think clouds are in the gaseous state. They're actually liquid droplets that are floating. So they may actually be in the liquid state. Anyone correct me on that if I'm wrong. Some of the, so that would be, these would, I believe, are stratus clouds. If you have cirrus clouds, they may be in the solid ice state and floating around. But the moisture you can't see, the humidity in the air, I believe, is in the gaseous state. Oh, here it is. Note that clouds are actually comprised of either very small liquid droplets or solid water crystals. Gaseous water in our atmosphere is not visible to the naked eye, although it may be sensed as humidity. Okay, so I'm glad I read the caption just to make sure that I understood that correctly. Yeah, I still remember some of my old aviation training, the different kinds of clouds. Anyway, okay. That water is a liquid at moderate temperature, will freeze to form a solid at lower temperatures and boil to form a gas at higher temperatures, figure 1.5, are macroscopic observations. But some properties of water fall into the microscopic domain, what cannot be observed with the naked eye. The description of water as comprising 2 hydrogen atoms and 1 oxygen atom, and the explanation of freezing and boiling in terms of attractions between these molecules is within the microscopic arena. The formula H2O, which can describe water at either the macroscopic or microscopic levels, is an example of the symbolic domain. The abbreviations G for gas, S for solid, and L for liquid are also symbolic. And wow, we have reached the end of lecture, the lecture one, but we have exercises. So let me, that was not too painful. Let me see now the exercises. We'll do the odd ones first because that app happens to have an answer key, and I feel more comfortable giving answers that are corroborated independently elsewhere. We can try to do the other ones, and I can't vouch for, I have nothing to corroborate whether I'm right or wrong. So just if you disagree with my answers, that's fine. Please post something in the video description. I mean, in the comment section of this video. So 1.1, chemistry in context exercises. Question 1, explain how you could experimentally determine whether the outside temperature is higher or lower than 0 degrees Celsius or 32 degrees Fahrenheit without using a thermometer. My guest answer was you could just take water and liquid water and put it outside. If it freezes, it's below freezing. So let's see the answer. It said place a glass of water outside. It will freeze if the temperature is below 0 degrees Celsius. Actually, I would not advise that. You could probably break the glass. Use some other container. All right, that was a bit of a snide remark, but I just thought I'd point that out. Question 3, identify which of each of the following statements as being the most similar to a hypothesis, a law, or a theory. Explain your reasoning. Okay, I'm going to guess at this first, and then we'll see what the answers are. A, the pressure of a sample of gas is directly proportional to the temperature of the gas. The pressure of a sample of gas is directly proportional to the temperature of the gas. That, I would call that a law. It relates to the ideal gas law. Now, the ideal gas law actually includes volume, so just a little caveat there that that statement is not actually complete, but I'll call that a law. So A is a law. A is a law. Let's see what it says. The answer key states that A is a law. It states a consistently observed phenomenon can be used for prediction. So let's look at B. Matter consists of tiny particles that can combine in specific ratios to form substances with specific properties. That doesn't seem very exact. I would classify this in the realm of hypotheses. Matter consists of tiny particles. That's kind of like a conjecture. So I'd say that's a hypothesis, and that can be subject to further experimentation and observation. So let me check the answer key. B, it says B is a theory, a widely accepted explanation of the behavior of matter. It says it's a theory. It is not a hypothesis. It is a widely accepted explanation of the behavior of matter. So I got that one wrong. I knew I wouldn't do well on these kind of big overarching questions. All right, so let's look at C. At a higher temperature, solids such as salt or sugar will dissolve better in water. I would put that as a hypothesis. At a higher temperature, solids such as salt or sugar will dissolve better in water. And the answer key says it is a hypothesis. A tentative explanation can be investigated by experimentation. Now, for going back to B, that really does sound more like a hypothesis. The distinction between hypothesis and theory is not, I didn't feel that was extremely clear in the text. But in terms of learning basic chemistry, I doubt that distinction will be very important. Most of what will be studied in chemistry deals with predictable behaviors, which would be very close to laws. Okay. So let's look at number 5. Identify each of the underlined items as part of either the macroscopic domain, the microscopic domain, or the symbolic domain of chemistry. For those in the symbolic domain, indicate whether they are symbols for a macroscopic or microscopic feature. A certain molecule contains one H atom and one Cl atom. H is in the symbolic domain. And since we're talking about a single molecule, that's a microscopic feature. So let's look at the answer key. For number 5, A is symbolic, and it is microscopic feature. Copper wire has a density of 8 grams per cubic centimeter. A wire is in the macroscopic domain, since you can see it. So let's look at the answer key. B, it is macroscopic. The bottle contains 15 grams of Ni powder. Ni, I believe, is the symbol for nickel. And since we can observe that it is powder and that it's 15 grams, we can weigh it. I put this, first of all, I'd say that this is symbolic, since it uses a name from a symbol from, it uses a symbol from the periodic table, and it is a macroscopic feature. So let's look at the answer key. C, it is symbolic and macroscopic. And finally, D, a sulfur molecule is composed of 8 sulfur atoms. Now, they are not using the symbol for sulfur, which is S, but they are going into the microscopic domain. So I'll call this a microscopic. I'll call this a microscopic domain, but not symbolic. Let's look at the answer key. D is microscopic, so I got that right. Just for your reference, to my knowledge, I've never been tested on this. I got A's in chemistry. I never got beaten down in terms of making the distinctions of symbolic, macroscopic, microscopic. But I think this is still helpful. This is really helpful to kind of distinguish things. I'm glad that they're doing it. All right, and the final question is, the amount of heat required to melt 2 pounds of ice is twice the amount of heat required to melt 1 pound of ice. Is this observation a macroscopic or microscopic description of chemical behavior? Explain your answer. I'd say, since we can visibly see the ice and also measure the heat, like say with a meter, the amount of heat utilizes in terms of joules, or we could alternatively express it in terms of watt seconds. I knew that from physics. I would say this is a macroscopic description of chemical behavior. And the answer is macroscopic. The heat required is determined from macroscopic properties. There, that wasn't, I don't think that was too bad. And I think the distinctions will start to become clear as we work with this. And as I said, in my background with studying chemistry, I honestly don't recall it from the chemistry classes I took that went into these details. But I think that's still kind of nice to explore it. Okay, let's go to the even questions. And as I said, I'll give my guess, but if you disagree, that's fine. I don't have anything to corroborate what I have to say. But just as an exercise, I think it's good to go through the even ones. It says, identify each of the following statements as being similar to a hypothesis, a law, or a theory. Explain your reasoning. Falling barometric pressure precedes the onset of bad weather. Now, I really don't like, I would say this tends to be a law. We do know that falling barometric pressure leads to, you'll see that when there's an onset of a storm. But bad, that is such a general qualification. So I'll call that a law. I'm not, I don't like the wording at all. B, all life on Earth has evolved from a common primitive organism through the process of natural selection. I would call that a theory. And some of you who know me know that I don't think, I'll call it a theory, but I don't think it's a correct theory. And C, my truck's gas mileage has dropped significantly, probably because it's due for a tune-up. I'd say that's a hypothesis. One could actually, there could be other causes for the gas mileage decreasing significantly, and that's subject to further observation and experimentation. Number 4, identify each of the underlined items as part of either the macroscopic domain, the microscopic domain, or the symbolic domain of chemistry. For any in the symbolic domain, indicate whether they are symbols for a macroscopic or a microscopic feature. The mass of a lead pipe is 14 pounds. So since we can see a lead pipe, I'll call that a macroscopic domain. That's something in the macroscopic domain. The mass of a certain chlorine atom is 35 AMU. That's atomic mass units. The mass of a certain chlorine atom is 35 AMU. Since it refers to a chlorine atom, that is a microscopic domain. And since we're not using any symbols, it's not in the symbolic domain. However, let's look at C. A bottle with a label that reads AL contains aluminum metal. Since we have a symbol, a chemical symbol, which is Al, this is in the symbolic domain. And since we're dealing with an entire bottle, we can say this is a macroscopic feature. D, Al is the symbol for the aluminum atom. So I would say this is in the symbolic domain, and it even uses the word symbol. And since we're talking about an atom, this is in the microscopic domain. And then finally, the last even question. According to one theory, the pressure of a gas increases as its volume decreases because the molecules in the gas have to move a shorter distance to hit the walls of the container. Does this theory follow a macroscopic or microscopic description of chemical behavior? Explain your answer. Whoa, this is, again, a little bit of a, I think it's a little bit of a confusing question. And so a lot of things in college often deal with being presented with questions that are not very clear and you have to take a guess. I really don't like that. If I write test questions, I try to make it clear and not to be ambiguous. But as someone having studied statistical mechanics, where we try to explain macroscopic behavior in terms of microscopic behavior, I'd say that the description in terms of molecules in the gas having to move a shorter distance to hit the walls of the container is a microscopic description that explains the macroscopic properties. That's the way I would have it in terms of a physics class. And I wouldn't describe that as a chemical behavior. So that's one of those questions. I'm glad, you know, I would just say it's not a well-stated question. And I have a pet peeve about questions that are kind of ambiguous and subject to too much interpretation. That's one reason I like mathematics. When the professor asks you to calculate something or to make a derivation, there's not any doubt about what is the right or wrong answer. So word problems like word questions like this can be challenging, but that's nothing I believe that's anything to stress about. Most of the chemistry exams I've dealt with, you're either naming a chemical substance or the reaction or calculating numbers. Some of these more questions about description and classification, I haven't seen them arise, but I still think it's a great exercise to try to understand the world. Before I close, I'll say that's one thing that's very impressive about chemistry. For a long time, we didn't have the instruments to see individual molecules. We now have electron microscopy that can see very large molecules. But before that, we had to imagine, based on observation of macroscopic properties, what was happening in the microscopic realm. And that was very difficult. And it's very satisfying that we were able to make these models of what was happening in the microscopic realm, and being able to create models that would make tremendous predictions about behavior of matter. And it was later confirmed by some of our observations when we started to get devices like electron microscopy. So with that, that takes us to the end of lecture 1.1, which was chemistry in context. So thank you for joining me in this video segment. Take care and God bless.